Hi, I'm Sang-Yup, and I'll be talking about our paper, Can We Find the Strong Authority Cat in Generative Models? This is joint work with Yujin Chang, Ji-Yong-sun, Dong-Yun Han, and Jae-Jun Yu. First of all, the answer to our title is yes. The presentation will focus on the existence of strong authority cats for generative models, how to find them, and further exploration of them. Hereafter, I will elaborate on those. Okay, let's begin with our motivation. As you know, state-of-the-art generative models tend to use extremely large and complex structures for better performance. However, since they require a lot of computational cost and memory, it is limited to apply to resource-constrained environments such as portable devices. To address these problems, several methods for pruning generative models have been proposed. However, it still has various limitations, such as complicated training or significant performance degradation. So let's talk about why pruning generative models is challenging. We consider three main reasons. First, unlike classification tests, generative models are unsupervised learning. In other words, there are no obvious criteria for what to prune in generative models. Second, compressed GANs have unstable training and performance degradation. Finally, generative models are mostly decoder structures. As a result, it is difficult to apply the traditional method focusing on this matter. For these reasons, pruning generative models is extremely challenging. To prune generative models stably, we propose to find strong authority cat in generative models. Strong authority cat means that we can obtain good subnetworks from randomly initialized networks without any weight update. This animation is showing strong authority cats intuitively. The left figure is a trained network that shows good performance, and the right figure is an overparameterized random network that shows poor performance. We can obtain the subnetwork from a randomly initialized network. As you can see, there is a very low probability that the subnetwork is equivalent to the left trained network. In other words, the subnetwork shows good performance without any weight update if we find it carefully. And this is a strong authority case. A key problem is how we can find strong authority case. One way to solve this problem is edge-pivot algorithm, which consists of two steps. First, we assign scores as to the randomly initialized weight omega. In this algorithm, scores mean the importance of weights. Next, we obtain a mask M by remaining the weights with the type K% highest score in the corresponding layer. And then we can obtain a sparse subnetwork by performing an element-wise multiplication between a mask and weight. However, one question still remains. How can we assign appropriate scores for the weights? In this algorithm, we compute the loss of the subnetwork and update our scores by using backpropagation. However, mask function h of s always has a zero gradient. To handle this function, we use straight-throw estimator. Consequently, we can express the amount of changes in the scores as this equation. This is important because it means that we need a proper loss when updating the scores. However, as I mentioned before, generative models don't have obvious criteria. Although universal loss is popularly used for training, it is extremely unstable to find proper scores. To properly update the scores, we utilize a corner maximum mean discrepancy. In this method, generated images and real images are embedded in feature embedding space via fixed feature extractor such as VGG or ResNet. In the feature embedding space, we can guarantee that the two distributions are the same if all other moments of those are the same. Unlike adversarial loss, the corner MD method guarantees stable convergence. In this slide, we show a schematic overview of our method. First, we assign random scores and obtain the arbitrary subnetwork according to scores from the randomly initialized network. And then in the feature embedding space, we optimize the MMD loss to update the scores. So we update the mask via scores. From now on, I would like to talk about our experimental results. Our first experiment is a very simple and fundamental question. Can we find strong authority tickets in generative models? To find the meaningful subnetwork, we test the performance of the subnetwork by changing the remaining weight k. When most of the random weights remain, the subnetwork shows poor performance. In this region, the subnetwork is similar to a random network. If k is 100%, it is the same as a random network. Therefore, it is natural that the performance of subnetworks is poor. These animations indicate how the performance of our subnetwork changes as a function of remaining weight k. As k decreases, the subnetwork shows a good generative performance. Even when k is 10%, it almost matches the performance of the pre-trained dense network. That is, in this region, we can find strong authority tickets. The similar trend is observed in precision and recall. The left images are generated by dense GFMN that use 11 million parameters, and the right images are generated by strong authority tickets that use 1.1 million parameters. We can see that strong authority tickets make good images with pure parameters. We performed the same experiments on SNGAN and BGAN for CELOP-A dataset and observed a similar trend. Through these experiments, we show that our method can find strong authority tickets regardless of dataset and generator architecture. Till this slide, we have observed the existence of strong authority tickets. Let's move on to the next experiment. As I mentioned before, our method is proposed to obtain right-weight networks from randomly initialized network. I'd like to expand on this aspect. The question arises whether our method can obtain lightweight networks from pre-trained models. So the second simple question is, can we use our method to write the pre-trained models? To investigate this question, we apply our method to the pre-trained generator. As you can see, we can obtain superior subnetworks that are lighter and more powerful than the pre-trained dense network via our method. We can even obtain a 5 times more efficient subnetwork than a dense model while maintaining the performance. In the extremely sparse region, the subnetworks show reduced performance. One reason for this is that there are too few remaining weights. Before I move on, I'd like to recap the main points. First, we can find strong authority tickets stably via our method. Second, our method can find remarkably more efficient networks from pre-trained models. Okay, let me turn to the issue of fine-tuning. In the previous experiments, we obtained the subnetwork from the dense network without any weight update. However, we are concerned that the weights may be too random or overfitting for dense structures. Therefore, we wonder if we can improve the performance of the subnetwork even more by fine-tuning the remaining weights. In other words, the final question for research is what happens when we further train a strong authority tickets. As you can see the left figure, imperial subnetwork can be improved by fine-tuning the remaining weights. However, the performance of strong authority tickets cannot be improved. The right figure shows that the performance of the superior subnetwork in our areas cannot be improved. It seems to us that the subnetwork cannot be fine-tuned because it has already achieved the best performance that it can have. Let's now take a look at the additional results. As I mentioned before, Although generative models commonly use adversarial loss, it was too unstable to find strong authority cats, so we utilized a corner MMD loss to find strong authority cats stably. In these experiments, we check if we really have to combine edge pop-up and moment matching. This figure indicates a visualization of the image generated by the subnetwork with adversarial loss. As you can see, the adversarial loss failed to find strong authority cats due to instability. On the other hand, our method guarantees stable convergence by optimizing an objective function. These figures indicate the convergence of our method. Therefore, we have to combine edge pop-up and moment matching. In this slide, I would like to talk about one nice property of our method. As you saw earlier, our method can find strong authority cats in the dense network by selecting appropriate masks. Thus, our method can generate new domains by finding only new masks for new domains. Finally, I would like to summarize the main points of this presentation. First, we experimentally showed that strong authority cats exist in generative models. Second, we propose a method to stably find strong authority cats in generative models. Finally, we further find that our method can even improve pre-trained generative models. This is the end of my presentation. For more details, please visit our project page where you can find our code, posters, and supplementary results. Thank you for your attention.